Hello and welcome my dear students. How are you? This is Varsha, your maths teacher. I'll be teaching you the topic matrices. Today not teaching, actually just summarizing the entire chapter in within 1 hour. It's a task because I feel like okay, I should take this type of question, that type of question, but yes, thanks to my experience that I have selected all the important ones which will cover the entire chapter for you. As everyone know, I like to keep it crisp, so I won't be wasting any time here and there. What I'll be doing is I will be noting each and every point, writing down all the important points of the chapter, in short summarizing the chapter. You can also write along with me. Hope that you have already attended the session somewhere and here you are there for revising the chapter. This will be really helpful for all of you who is looking for short term and more gains. So starting with the introduction of matrices, people. Starting with the introduction of matrices, what is matrices? Matrix is a singular form and matrices is a plural form. It is nothing but rectangular array. It is rectangular array. Array is arrangement. Rectangular array of what? Of elements or functions. Functions like any of your sine, cos, tan, trigonometric functions, GIF functions, any kind of function that you have studied, polynomial, identity, etc. So it's a rectangular array of functions. A matrix is denoted or written in square bracket like this, or some of the old textbooks also follow this kind of round bracket to denote a matrix. Next one. A matrix is named with capital letters like A, B, C, X, Y, Z, just like your sets. The name of a matrix is done. Now you have to give the address of a matrix. So order of a matrix is nothing but M by N. Remember, this is M by N, read as by, not M into N, M by N. Where what is M? M is the total number of rows in a given matrix, and N is the total number of columns in a given matrix. Rows means the horizontal ones, column means the vertical ones. So order is written at the base. Towards the base you write the order of the matrix. Now within a matrix, once you know the address of the matrix, you need to know the address of each element in the matrix. So element in a matrix is written by Aij, where I denotes the row position and J denotes the column position. Like I will tell you in which row the element is present, J will tell you in which column the element is present. Using this basic information, question like construct a matrix can come, or what is order of a matrix. Order of a matrix will also lead to one formula, total number of elements in a matrix. So total number of elements in any matrix will be Mn. You simply multiply their orders, M into N, like 2 by 3. If it is 2 3s are 6 will be total number of elements in any given matrix. That's all about the introduction to matrix. Let's move to the next slide. What was the next thing we studied in matrix? Types of matrices. Matrix, matrices, whatever you write. Did I underline there? Yeah. So how many types of matrix did we study? Let's write down all of them one by one. The very first type was your zero or null matrix. No, that was not the first type. The very first type was the row matrix. What does a row matrix mean? A row matrix simply means when your Aij, the matrix, has only one row and the number of columns can be anything. Example, this is the structure of a row matrix. Second one, column matrix. Column matrix is when the matrix has only one column, number of rows can be anything. Something of this format. Third one, square matrix, meaning when in a matrix M and N are equal. This is I and J, guys. M and N are equal. When M is equal to N, number of rows equal to number of columns, we say it's a square matrix. Now from square we will get a diagonal matrix, right? So what is a diagonal matrix? Okay, before I go ahead, there are certain things about a square matrix which we should know. A square matrix will look like this: number of rows, number of columns equal. A11, A12, A13, A21, A22, A23, second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column. Correct? Order is 3 by 3, 3 rows and 3 columns. In this, people, in this, you can see two diagonals, the blue one and the orange one. Everybody can see two diagonals, blue and orange. The blue diagonal is called as the leading or principal diagonal. Leading or principal diagonal, and henceforth I will refer to it as only diagonal. When I say use the word only diagonal, I am talking about leading diagonal. Why it is called as a leading diagonal? Because in that I is equal to j. 1, 1, 2, 2, 3, 3. The other one, the orange one, is called as the off diagonal. Off diagonal. Not the lagging diagonal, it's an off diagonal. Right. That also leads to one important thing. What is trace of a matrix? Trace of a matrix is sum of all leading diagonal elements. Sum of all leading diagonal elements is called as trace of any given matrix. So this diagonal, leading diagonal, is always present only in case of square matrix wherein the M and N are equal. Okay, next. Square matrix. Next one that we want to see is a diagonal matrix. Now what is a diagonal matrix? So firstly, diagonal matrix is a square matrix. Every diagonal matrix has to be a square matrix. So a square matrix will become diagonal when the leading diagonals will be non-zero. When the leading diagonals will be non-zero, that is when I equal to j, it will be non-zero, and it will be equal to 0 when I is not equal to j. Can you understand this definition? When I and j are not equal, that is 2, 1, 3, 1, 3, 2, 2, 3, 1, 3, 1, 2. These elements, when I and j are not equal, it will be equal to 0. And wherever the I and j are equal, I 1, 1, 2, 2, 3, 3, it will be non-zero of this sort. Right? Okay, next. What is a scalar matrix? Now a scalar matrix is again derived from a diagonal matrix. So every square matrix can be converted into diagonal by making the non-diagonal element 0, and diagonal matrix can be converted into a scalar matrix. How? When you make all the non-diagonal elements same. That is, Aij will be 0 when I and j are not equal, and Aij will be equal to k when I and j are equal. When I and j are equal. Let me take an example here. It will be some fixed value k. Rest everything is 0. It's a diagonal, it's a square. But only difference is that's 0. Sixth one, it's further followed by scalar, which is identity matrix, also called as unit matrix. So unit matrix, firstly it's a scalar matrix which becomes diagonal by making other elements 0, then it becomes scalar by making diagonal same, then it becomes unit, right? And what is the definition? Aij, where it is equal to 0 when I and j are not equal, and it is equal to 1 when I is equal to j. So identity matrix can be of different forms, like I1 order is 1, I2 order 2, I3 order 3. We only have I1, I2, I3, and we will only be dealing with that. I am writing order 2 here. can you see all the diagonal elements, leading diagonal elements are same and they are equal to 1. So every unit matrix is also scalar, it's also diagonal, it's also square. Every scalar is also diagonal, also square. Every diagonal is also square, and square is a square. Anyways, the last one left is nothing but the first one which I wrote, 0 or null matrix, when all the elements are 0. Simply this is a 0 matrix or this is a 0 matrix. All these are examples of 0 matrix. All the elements are 0. Right? That's the type of matrix. What did we study after type of matrix? After studying the types of matrix, we went on to study operations on matrix. What kind of operations, guys? Let me know in the chat. Operations on matrix like, yes, addition, subtraction, equality, scalar multiplication. So remember, these operations on matrix are only possible when two matrices are of same order. That is, when A has an order m by n and B also has an order m by n. Right? When the orders are same, you can perform this operations. What are the operations? Let's list them down. So very first operation is equality of matrix. What is equality of matrix? When you equate any two matrix, what ultimately happens is the corresponding elements get equated. The first row, first column will get equated with first row, first column simultaneously. First element with first, second with second, and so on. We will see examples, don't worry. Similarly, guys, addition and subtraction. Addition and subtraction. That is A plus B. When you are adding two matrix and when you are subtracting two matrix, what happens? When you are adding Aij, the first element will get added with the first element of second matrix Bij, and similarly in subtraction Aij minus Bij, the corresponding element will get added and subtracted. Last, fourth one operation is scalar multiplication. Scalar multiplication means when you multiply any matrix with an element, when you multiply any matrix with some constant k is a scalar over here, k is a constant scalar. So what happens actually? Each element of the matrix will get multiplied with that scalar. Do you want me to take an example for this? Let's take it. So if I want to do 2, 1, 3, minus 9, 8, this 2 will get multiplied with each element, giving me 2, 2 3s are 6, 2 9s are minus 18, 2 8s are 16. Simple. Suppose if I want to add two elements like 1, 3, minus 9, 8, I want to add it with 2, 6, minus 18 and 16. The resultant will be 1 plus 2, 3, 3 plus 6, 9. Can you see corresponding elements? Minus 9, minus 18, minus 27, and 8 plus 16 will be 24. First added, second added, third, fourth. Basically, when you superimpose the two on each other, the elements at same position will get added, and if it is a question of subtraction, it will get subtracted. If it's a question of equality, similar way. Right? What was the next thing? After this, we went on to study multiplication of matrix. Very important, and I guess this is something which would have demanded some practice from your side. Am I right? This would have asked for good amount of practice from all of you, isn't it? Did you practice enough? Before I go to multiplication, I would like to write some laws. Laws of addition, subtraction, whatever we did so far. Let's write down the laws related to that and then move to next one. So A plus B is equal to B plus A. We know matrix addition is commutative. Is the subtraction also commutative? Is A minus B equal to B minus A? No, the subtraction cannot be commutative. Makes sense? Yes, guys. Next, A plus what will give me the answer as 0? A plus what will give me the answer as 0? A plus minus A. So what is minus A? Minus A is nothing but the additive inverse. Minus A is called as the additive inverse of matrix A. Next, A plus B plus C is same as A plus B plus C. That is, addition is also associative. It is also associative. Right, guys? Next, if there is K into A plus B, that is a constant is getting multiplied like this, you can write it as Ka plus Kb. K times A plus K times matrix B. A and B are two matrices. Next, if something like this, K plus L into A, where K and L both are constants, you can write it as Ka plus La, just like your numbers. K comma L are nothing but constants, any constant number. Okay, these are few laws related to additions. Can I go ahead? Okay, additive inverse. Please remember, this can be a 1 mark MCQ to all of you. Followed by that, I can make one more question. A plus what will give me the answer as minus A? A plus what will give me the answer as A itself? That means I'll get identical value. A plus 0 will give me the answer as A. So that means 0 is called as the additive identity. 0 is called as the additive identity. Please make a note of this. Identity because I am getting an identical output. Inverse because I am adding an inverse and getting a 0. Right? Okay. Next. Now I think we can go to multiplication. How do we do multiplication? What is the preliminary condition for multiplying any two matrix? The preliminary condition for multiplying any two matrix, suppose matrix A has an, this bracket is not correct, yeah, has an order M by P and matrix B has an order P by Q. Can we multiply these two matrix? Yes, we can multiply these two matrix and the answer will be, let's say, C. Matrix C whose order will be M by Q. So condition is number of columns of first matrix should be equal to number of rows of second. Number of columns of A should be equal to number of rows of B. Fine. Also the resultant matrix will have this as the order M by Q. That means to get C, which is multiplication of A and B, its order will be M by Q, number of rows and number of columns. That's what we do in matrix multiplication. What is exactly multiplication? When I multiply two matrix, I am actually multiplying row of A with column of B. Multiplying row of A with column of B, that is what the multiplication entire process is. We can take example to understand this right away in case anybody has smallest of confusion with this method. 3, 6, 9 minus 1, 2, 5, 6, 1, 1, 3, 0, 4, 1. Can I multiply? The first question is the multiplication possible? The multiplication is not possible. Why? Because it's 2 by 2 and it's 3 by 3. The number of columns and number of rows are not matching. So then what do I do? Okay, let's do one thing. Yeah. 6, 5, 3, 2. Now 2 rows, 3 columns. Now can I multiply these two matrix? Of course, ma'am, you can multiply. What will be the result of order of the resultant matrix? It will be again 2 by 3, that is 2 rows and 3 columns. Acha, let's see how to multiply them. In case at a very preliminary stage for students who are just starting to multiply, all you can do is make a skeleton matrix, because we know that the resultant will be 2 by 3, that is 2 rows and 3 columns. You know there will be 2 rows like this, A11, A21, 3 columns like A12, A13, A21, A23. Now all you have to do is find these 6 elements. Find these 6 elements. This is the answer. Find the 6 elements. For finding the very first element, which is A11, what you will do? 11 means first row, first column. Pick this first row, keep it on the first column. Like you take this first row and superimpose on the first column and multiply the corresponding elements. If you keep this like this, where is this? Yeah. 3 2s are 6, 6 1s are 6 and 3 zeros are 0. Right? First row, first column. So this is done. Now I want A12, that means first row, second column. Keep the first row on second column. 3 5s are 15, 6 1s are 6, 3 4s are 12. Done. Let's go for A13, that is first row and third column. Keep the first row on third column. 3 6s are 18, 6 3s are again 18 and 3 1s are 3. With this way, guys, you can never go wrong. This is a foolproof method because you're going one by one. Well, of course, this is not recommended in your exam. You should practice enough to do it without the need of this. A21, second row, first column, 9 2s are 18, 5 1s are 5 and 2 zeros are 0. Second row, second column, 9 5s are 45, here there is 0, right. 5 1s are 5 and 2 4s are 8. This is also done. Let's go for A23, second row, third column, quick. 9 6s are 5 3s are and what else? 2 1s are. We've got the answer, people. We've got the multiplication. 6 plus 6, 12. 15 plus 6 will be 21 plus 12, 33. 18 plus 18, 36 plus 3, 39. Here 18 plus 5 will be 23, 45 plus 5, 50 plus 8, 58 and 54 plus 15, 69 plus 2, 71 is what we get the multiplication of these two matrices. That's the procedure to multiply. Hope it's clear. If not, watch it on a recap mode or winding mode. Fine. Few properties related to matrix multiplication. Is A into B equal to B into A? No. Matrix multiplication is not commutative. It is not always equal. In some cases, yes, it can be equal. Those are special cases, but in general, AB and BA are not equal. What about AB into C? Is it equal to A into BC? Yes, it is associative. It is associative. You can do this, right? What will you multiply with A in order to get the answer as 1 by A? Or in general, we don't go for division. Many students ask, ma'am, we do addition, subtraction, multiplication, why not division? Because division is nothing but inverse. So instead of A into A inverse will give me I. A inverse is called as the additive identity, additive inverse. Additive inverse of multiplication. That was additive inverse, sorry, in other words I can write it multiplicative inverse. Not additive, multiplicative inverse. There it was additive inverse. Here it's multiplicative inverse. When I multiply A with its reciprocal, I get I. I is an identity matrix, right guys? Okay. What happens if I multiply A with I get back A. So what is I? I is multiplicative identity. If I get an identical term output, it's called multiplicative, not inverse, identity. So in addition, additive inverse was minus a and additive identity was 0. Here multiplicative inverse is a inverse, multiplicative identity is I. I hope this is fine, fair, good. One more property, a plus b into c is there. You can write it as AC plus BC. That is your distributive law. Is applicable here. Distributive law is also applicable here. Right, these are the properties of multiplication. What was the next topic after multiplication? After multiplication, we hopped on to transpose. Very easy, isn't it? Nice, sweet. Transpose. Transpose simply says that you interchange the rows and column. Interchange rows and columns. That means if matrix A has an order of m by n, its transpose will have an order n by m. Right? Transpose is written as A transpose or A prime. That's also a way to write transpose. Some properties related to transpose. Let's check. The properties related to transpose are, first one, A transpose, the whole transpose is same as A, just like your complement. When you take transpose twice, you get back the same thing. Second property, A plus or minus B, the whole transpose, will be equal to A transpose plus or minus B transpose. Third property, K into A, the whole transpose is same as K into A transpose. Okay. Last but not the least, the reversal law, A into B, the whole transpose is equal to B transpose into A transpose. This is called as your reversal property. If there are more than two elements like A, B, C, the whole transpose, you will start from the end, that is C transpose, B transpose, and then A transpose. Got it, people? These are the properties of transpose. With the help of transpose, the whole aim of transpose was to study about symmetric and skew symmetric matrix, right? That was the whole aim of studying transpose. Symmetric, skew symmetric. Symmetric matrix by definition says that when A transpose is same as A, we call it as a symmetric matrix, and skew symmetric by definition says when A transpose is minus of A, you get a skew symmetric matrix. To get into the detail, when Aij is equal to Aji, that is when A12 is equal to A21, A13 is equal to A31, and so on. Here a minus sign comes. When Aij is equal to minus of Aji, you say it's skew symmetric. I mean, to be honest, just by looking at the matrix, you understand whether it's symmetric or skew symmetric. Important point in skew symmetric is diagonal elements are 0. All the diagonal elements will be 0. Why? You just solve this. When you solve this, you will get 2 times Aij equal to 0, that is Aij equal. Okay, let me help you. For diagonal elements, I is equal to j. Substitute here. Aij is equal to minus of Ai. I equal to j. Let's substitute I equal to j. Ai is equal to minus of Aii. 2 times Aii equal to 0. That means Aii equal to 0. What is Aii? Ii means I equal to j. That means diagonal element equal to 0. That is what it's trying to tell us. If I want to take an example, symmetric matrix, the diagonals can be anything. 3, 11, 15. But yes, if there is a 4 over here, this position should be minus 4. If there is a 6, minus 6. And if there is 13, minus, oh my god, this is wrong. We don't get minus sign, right? We get the same things. We get the same things here. Oh my god. We are talking about symmetric. So this was 3, 6, 9. Let's suppose if this is 11, this should also be 11. If this is 4, this should also be 4. And if this is 13, this should also be 13. This is an example of symmetric matrix. And for skew symmetric matrix, first thing to notice is that the diagonals will be 0. And then of course opposite signs. 3 minus 3, 4 minus 4, 15 and minus 15. Something of that sort is your skew symmetric matrix. Got it, people? One formula related to skew symmetric matrix that we study, we know that A plus A transpose will always be symmetric and A minus A transpose will always be skew symmetric. Oh my god, I've been talking for 5 hours now. So, whenever a single matrix has been asked to represent in the symmetric and skew symmetric form, suppose a matrix A is asked to be represented in symmetric and skew symmetric format. You can write A is equal to half of A plus A transpose plus half of A minus A transpose. Note down this formula where A plus A transpose means symmetric and A minus A transpose will be skew symmetric. Right, guys? Okay, let's move on towards the last part. We have already finished half an hour of this session. I guess we should be going to the questions now quickly. Right, elementary operations. There are some elementary operations also which is allowed in matrix in order to find the inverse of a matrix. What are the elementary operations allowed? Whatever I am writing for row is also applicable for column. First one is Ri interchanged with Rj. That means you can interchange any 2 rows or any 2 columns. Second one, Ri changes to 3 times or k times Rj. That means you can multiply any given row with a constant. You can multiply any given row or column with any constant. K can be any constant. Don't make it 1 by 0 now. Ma'am, K is 1 by 0. So everything becomes not defined. No, don't do that. And third one, Ri changes to Ri plus K times Rj. Similarly, Ci changes to Ci plus K times Cj. It's very important to note that here there is Ri, here also it should be Ri. Some students write it the other way around. R1 changes to R1 plus 3 times R2. This is fine, allowed. R1 changes to R2 plus 3 times R9, not 9, R3. Is it allowed? No. If you're changing R1, you have to take help of R1. Similarly, if you're changing, let's say C1, you have to take help of C1 to change it. The second one is not allowed. Whatever you're changing should be present on the right hand side. And whenever you're solving a question using elementary transformation, do not use both the transformations in a single question. It will go wrong. The next topic is about inverse. The last topic is based on inverse. What is inverse of a matrix? That is what your division can be called as. So when you multiply any matrix with another matrix B and the resultant is I. A into B or B into A gives us I. That means B is inverse of A or A is inverse of B. Right. In other words, inverse is written like this. The inverse of A can also be written like this. B equal to A inverse. Some things related to inverse. A into A inverse will be I. Or A inverse into A will also be equal to I. A inverse, the whole transpose is same as A transpose, the whole inverse. Okay. Next, A inverse, the whole inverse is same as A. When you take the inverse twice, you get the same thing. Remember, when you are doing pre-multiplication and post-multiplication in matrix, it means two different things. Suppose you are doing pre-multiplication, pre-multiplying by A. So ensure that, suppose if it's AB equal to I, you're pre-multiplying with A inverse, it has to be before. It has to be before. And if you're doing post-multiplication, post-multiplying by A inverse, it has to be after AB. That is, AB into A inverse is equal to I into A inverse. This is used in some quadratic equations of matrix solving, right? Some matrix solving wherein quadratic equations are involved. Fine. One couple of more things related to this I want to tell. That is, whenever you are doing elementary transformation to find inverse, how to find inverse. So if you are doing row transformation and column transformation, you understand any one very well, the other part will be very easy to understand. So row transformation, suppose you are doing row transformation, you must have noticed that what we do. Suppose for 3 by 3, if you are doing it for a 3 by 3 matrix, 9 elements are there. What should be made 1 first? What should be made 0 first? That's the biggest challenge, right? And that's the part, if you crack it, the question is done. If you crack that part, the question will be done. So while solving row transformation, the first thing which we do is make this one. Make this one. Then we go down, make this and these two zeros. You make these two elements 0 with the help of this one. Next, after making these two elements 0, we go here and make this central element 1. Then up and down, we go and make them 0. Up and down, we go and make them 0. After doing that, we come down here and make this element as 1. Then again, these two elements are made 0. That's how we convert any given matrix A into an identity matrix. You must be remembering how we use this. So in order to convert any matrix into identity matrix, follow this W pattern. 1, 2, 3, 4, 5. Follow this W pattern. You will never ever go wrong. Trust me on this blindly. This is for row transformation, and similarly if you are doing a column transformation, guys, I need not draw this because ultimately we are aiming for an identity matrix and which is already present on the left hand side. Yeah. So in case of column matrix, if you want to make this an identity matrix, this is any matrix A. First step is you will make this element 1. Then you will go here, make these two elements 0. If it's column transformation, go row wise. If it's row transformation, you go to column. You change the column. Here if it's column transformation, you change the row. Or, right? First row done, now go to the next row. This. You will make this as 1 and then these two elements as 0. Follow the arrows. You'll first make this one and then corresponding elements of the row 0. Then finally you'll make this element as 1 and corresponding elements of the row will be made 0. So whichever row you are targeting, target the 1 first and then go for 0. For second row, target the 1 and then go for 0. Third row, target the 1, then go for 0. So in column transformation, that's why I said we go row wise. And if it's row transformation, you target the first column, make 1, then zeros. Target the second column, make 1 and then zeros. Target the third column, make 1 and then 2 zeros. This is the approach and the step you all know very well. Do I have to write it? Let me write it. In case of row, suppose you write A into A. Yeah, A into A inverse is equal to I. We know this, right? You substitute the value of A given to you. A inverse is kept as it is, like a showpiece. Like a showpiece, A inverse is kept, isn't it? You will substitute the value of A and you will substitute the value of I. A inverse is kept as it is. Now you will do some transformation to make this A as I. You will try to make this A as I. This A is made I. How? I showed you just now. So you'll do some transformation, make this A I. A inverse is already there, and this will convert into something like a B. I into A inverse is nothing but A inverse, and you will get your A inverse on the right hand side. Similarly, for column transformation, you will do this. A inverse into A is equal to I. Keep A inverse as it is, like a showpiece. Substitute A and I. Substitute your A and I. Dun, 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 dun. Do some column transformation. What column transformation? Like this, and make this A equal to I. A inverse is already there, and this will turn into some other matrix called as B, because whatever transformation you are doing, it will be done on both left and right side. It will be done both on left and right side, isn't it? Of course. Now A inverse into I is nothing but A inverse. A inverse is equal to B. We get the answer. So both ways are very symmetrical. Understand one very well and go for the other. Is that clear? Can I go to the questions now? Finally, yes. Let's do it, guys. Oh yeah. So very first question, using elementary transformation, use the operation rho 1 changes to rho 1 minus 3 times rho 2 in the following question. Looks very easy. Try to answer it. I bet you're going to go wrong. 4 2 3 3 1 2 0 3 2 0 1 1. The answer to this is rho 1 changing to rho 1 minus 3 times rho 2. So there I'll change the rho 1. If because I'm changing the rho 1, let's write the rho 2 as it is. No touching for rho 2. 1 1 0 3 3 3. Rho 1 minus 3 times rho 2. 4 minus 9 minus 5. 2 minus 9. Yeah, minus 7. Then 1 minus 0, 1, and 2 minus 9, minus 7. What about this 2 minus 3? No, we are not going to do 2 minus 3, guys. This will remain as it is. When you have anything of this format, suppose x is equal to AB, and you are applying some transformation, x will change, A will change, but one of them will not change. When you apply a transformation, not all three will change. Left side, right side will change, but on the right, if there are two, only one will change. Similar thing we did in row transformation and column transformation just now on the previous slide. So here also the third one will remain as it is, and that is present in option A. Am I correct? Yes, boss. Please note this point. All the questions that I've taken are super interesting, and we get to learn something from each question. I wish I am able to do all the questions. The first, 2x 3 1 2 minus 3 0 x 8 equal to 0. Find the value of x. It's matrix multiplication. Keep the orders in mind. 1 row 2 columns, 2 row 2 columns. We can multiply. The resultant will be 1 by 2. So first row, first column. 2x into 1, 2x. 3 into minus 3, minus 9. First row, first column done. First row, second column. 2x into 2, 4x. 3 into 0, 0. So that's your 1 by 2. Again, it is multiplied with another matrix x and 8. What are we getting? First, this is 2 by 1. 2, 2, same. Of course, we can do the multiplication because resultant is 1 by 1. First row, first column. 2x minus 9 into 8. 2x square minus 9x. 4x into 8, 4 8s are 32x is equal to 0. Right? Yeah. 2x square minus 9x plus 32 will be 7, 8, 9. Yeah. 23x. And yeah, x common. 2x plus 23 equal to 0. That means x is either equal to 0 or x is equal to minus 23 by 2. That's it. Done, done, done. Got it? Very nice. Next, PQ is given. Prove that PQ is equal to something and it is equal to QP. People, remember that whenever you multiply any two diagonal matrix, the diagonal elements get multiplied. Yes. So if you are doing P into Q, X into A is what you will get. Rest everything will be 0. That's a shortcut, please remember. Y into B and Z into C. Similarly, when I am doing Q into P, this is Q, this is P, I'll get AX, right guys, BY and CZ. Are the two things same? Yes, YB and BY are same. We know multiplication is commutative that way. These elements are nothing but same. So hence proof, done. So what we learned in this question, matrix multiplication of diagonal matrix simply multiplies the diagonal elements. We'll go to this. If A is a symmetric matrix, then what is the value of X? If A is a symmetric matrix, then these two elements should be equal. X minus 1 should be equal to 2x plus 3. 2x minus x is x. Minus 1 minus 3 is minus 4. X is minus 4. Option C. You must be wondering why I skipped the previous question. It's a little lengthy. And let's see if we get some time for that. Interesting. A is 1, 2, 2, 1. F of x is 1 plus x into 1 minus x. Find out f of A. Find out f of A, people. Now this is x, this is A. How is it related to f of A? Something confusing, right? Think about it carefully. F of x is nothing but 1 minus x square. Now this A here actually is capital A. So f of capital A is equal to 1 minus A square. F of A is 1 minus A square. A is in numeric system. Capital A is in matrix system. Please remember that I in numeric matrix system is similar to 1. I is similar to 1. Identity matrix is similar to 1. So here f of A, if I want to find out, 1 means I and this is A square. The question is actually you have to subtract A square from identity matrix. 1, 2, 2, 1. Everybody, now your power of multiplication should be seen. Firstly, the multiplication will happen and then the subtraction should happen, of course, right, to get the answer. So, power of multiplication and subtraction both. First row, first column, 1 ones are 1, 2 twos are 4, 1 plus 4, 5. First row, second column, 1 twos are 2, 2 ones are 2, 4. Second row, first column, 2 ones are 2, 1 twos are 2, 4. Second row, second column, 2 twos are 4, 1 ones are 1, 4 plus 1, 5. Now subtract 1 minus 5 minus 4, 0 minus 4 minus 4, 0 minus 4 minus 4, 1 minus 5 minus 4. Taking minus 4 common, you will get 1, 1, 1, 1. That is option number A. A is the answer. People, this was the trick to understand that the small a in numeric system is capital A in matrix system and I is nothing but 1. Let's do one question on elementary transformation also. We did about multiplication, equality, symmetric, skew symmetric, all of the types I'm just trying to cover. So this is one question on finding inverse using elementary transformation. A is given, whichever, row transformation, alright. What is A? 1, 3, 2, 7. A inverse is a showpiece. I is 1, 0, 0, 1. Now, first task, as if you recall, we have to make this 1, then go here, make this 0, then we will go here, make this 1 and then 0, right? Whichever, if it's a row transformation, we target the first column, make 1 and then 0. 1 is already there, hooray! Our task is to make this 0. How? Row 2 changes to row 2 minus 2 times row 1. Can you see? 2 minus 2 will give me 0. Wonderful. 2 minus 2, 0. 7 minus 6, 1. Wonderful. This is. Same thing should be applied on right side also. 0 minus, first row as it is. 0 minus 2 minus 2. and 1 minus 0, 1. Next, okay, 1 is done, 0 is done. Now this should be 1, okay, already there. Final thing, the upper element, this should be made 0. That means row 1 has to be changed in order to make this 0. How will you make this 0? By using the same columns 1. By using the same one, right? From this you have to make this 0. Look at the arrow. So row 1 changes to row 1 minus 3 times row 2. That will make sure that all other elements are not affected, otherwise you will end up making it a mess. Following that will always help. So 1 minus 0, 1, 3 minus 3, 0, 1 minus 3 times minus 2, that is 1 plus 6, 7, and 0 minus 3 is minus 3. This is identity matrix. I into A inverse is something like say B, and this B is nothing but the A inverse using elementary row transformation. Can we see this option anywhere? 7 minus 2 minus 3, 1, option A. Very good. If any matrix A is both symmetric and skew symmetric, what can you talk about it? If any matrix A is both symmetric and skew symmetric, by property, if it is symmetric, A transpose is A. If it is skew symmetric, A transpose is minus A. Equating both the things, A is minus A. 2 times A is 0 and A is 0 matrix. A is a null matrix. Option B is correct. Option B is correct for this question. Very good. Total number of possible matrices when the entries are 2 or 0 in a 3 by 3 matrix. In a 3 by 3 matrix, when the entries are 2 or 0. I just thought of taking this question because ultimately very obvious question and it shouldn't happen that I have not done it. Okay, the entries, there are 2 possible entries for each position in a 3 by 3 matrix. 2 possibilities in each position. Using your PNC, permutation combination concept, each position has 2 possibilities. So 2 into 2 into 2, total 9 positions. 2, 2, 2. So 2 raised to 9, which is 5 and 2. 2 raised to 9, which is 5 and 2. Got it? Do you want to do one interesting question, because then I am done. The answer to this was the last one which I left. I won't be able to sleep well if I don't share with you guys. Like I want to solve that question. Here it is. A is given and I is identity matrix. You have to prove I plus A is equal to I minus A into some matrix. We have to prove this, so let's take the LHS and find out what it has to say. I plus A. I is identity matrix. Guys, I'm not going to write everything now. You have to understand in your mind, I is 1, 0, 0, 1. A is given. So what will be the resultant? 1 plus 0, 1. This will be minus tan alpha by 2. 0 plus this will be tan of alpha by 2. This is alpha, not pi. This is alpha, not pi, people. And 0 plus 1 will be 1 over here. So this is the LHS, we have got it. Let's go for RHS. RHS is I minus A into something. Well, let's quickly calculate I minus A. Alert, it's going to be a little lengthy. I minus A, do it mentally. This is A present in front of you, right? Subtracted from I. 1 minus 0, 1. 0 minus of this will be I minus A, right? 1, 0. Yeah, this will become plus. And then 1, 0, 0. 0 minus tan of alpha by 2. And 1 minus 0, 1. This is what I get I minus A multiplied with cos alpha minus sin alpha plus sin alpha and plus cos alpha. Okay, this RHS needs some good solving. Shall I do it on the next page? Yes, why not? First row, first column, cos alpha plus tan alpha by 2 into sin alpha. Cos alpha plus tan alpha by 2 into sin alpha, right? I was right, yes. Go back, first row second column, minus sin alpha plus tan alpha by 2 into cos alpha, minus sin alpha plus tan alpha by 2 into cos alpha. Come back, second row first column, minus tan alpha by 2 into cos alpha plus sin alpha. Right people, just go back, check, plus sin alpha it was now. I wrote it the other way around, into cos alpha plus sin alpha, that is what it was. Going back, second row second column, minus tan into minus sin will be plus tan into sin plus cos. So tan alpha by 2 into sin alpha plus cos alpha. Let me just see if I am anywhere near what is needed. Looks like yes. Let's proceed and solve it, then we'll check out. Okay guys, cos alpha. Because there is one half angle like alpha by 2, we have to use the formula of half angle. Cos alpha can be written as 1 minus tan square upon 1 plus tan square. Or even if I don't write, I think it's fine. Cos alpha can be written as cos alpha for now. Tan alpha by 2, let it be. Sin alpha can be written as 2 sin alpha by 2 into cos alpha by 2. Great. Tan alpha by 2 can be written as sin by cos, isn't it? Sin alpha by 2 upon cos alpha by 2. This one cos will cancel. Here you can see sin square alpha by 2. So in the next step, I am going to write this cos alpha as 1 minus 2 sin square alpha by 2, and this is 2 sin square alpha by 2. This minus plus will cancel, and in the final step I'll get 1. Fine, I have just dealt with one element so far. Cos alpha as cos alpha, tan as sin by cos, sin as half angle formulae. Cos cancel, this is sin square. So immediately I saw sin square, I realized that okay, cos can also be written in terms of sin square as 1 minus 2 sin square. We cancel, we got 1. Similar thing can be done here. Can you see this? Very, very, very same. Same. So here also I'll get a 1. I think that's pretty understood. This will also be like 1 minus 2 sin square alpha by 2 plus 2 sin square alpha by 2, and you will get the same thing. 1 you will get. Fine. Cool. Let's deal with the other two elements now. Minus sin alpha plus tan alpha by 2 into cos alpha. This is a little tricky. Minus sin alpha can be written as minus 2 tan alpha by 2 upon 1 plus tan square alpha by 2, the half angle formulae. And here it is already plus tan alpha by 2. Cos alpha can again be written as 1 minus tan square alpha by 2 divided by 1 plus tan square alpha by 2, isn't it? Denominators are same. Try to simplify the numerators. Now matrix has gone somewhere else only. Matrix has gone somewhere else. I am taking this separately and solving, because whatever you will get this similar to this. This is equal to minus 2 tan alpha by 2, multiplying this inside, plus tan alpha by 2 minus tan cube alpha by 2 divided by 1 plus tan square alpha by 2. Minus 2 plus 1 is minus tan alpha by 2. If I take minus tan alpha by 2 common, in the bracket I will be left with 1 plus tan square alpha by 2. Denominator is also 1 plus tan square alpha by 2. This gets cancelled and I will be left with minus tan of alpha by 2. Perfect. I am left with minus tan alpha by 2 here. Minus tan alpha by 2. Minus tan alpha by 2. And the only difference between them is a matter of sign. Here sign is negative, here sign is positive. So because negative, I got negative tan alpha. In the other case, we would end up getting positive tan alpha by 2, and that's nothing but the LHS. Here we are getting 1. This is equal to LHS. RHS is matching with the LHS, hence proved. Go through it once again for your own sake. LHS was pretty simple, straight. RHS I minus A is this matrix, and this is a given matrix. Multiplication, do it carefully, you will get this. First, these two, try to solve them. They are ending up to be 1. Very simply, cos alpha is 1 minus 2 sine square, tan is sine by cos, and sine as 2 sine cos. So that is easy. Come for this, minus sine alpha can be written as minus 2 tan upon 1 plus tan square, a formula. Tan alpha as it is, cos alpha is 1 minus tan square upon 1 plus tan square. Then denominators being same, you bring it together, and numerators you multiply, open the bracket. Minus 2 plus 1 is minus 1, take it common, inside 1, and from here plus tan square is left. Numerator denominator cancels and you get the answer. Got it? So that was all for this chapter from my side. I think I have covered it from all aspects as far as possible. If anything missing, do let me know in the suggestions, in the comments. I will be willing to work upon it. And thank you for patiently watching the entire session. Means a lot to me, guys. Thank you. See you in the next session with another chapter, and I'll try to include more fun. Because it was the first session, I thought I will show my talent of teaching. Later on, definitely you'll see my talent of, Chalo. Goodbye. Thank you. Take care. Have fun.